Welcome everyone to the SimScale webinar on energy efficient water pump design using simulation on the cloud. I'm Kanchan Garg, Product Manager for Rotating Machinery at SimScale, and co-presenting with me today is Omar Abid, Application Engineer with SimScale. Before we begin, might I please remind you all that your mics are going to remain in mute. Should you have any question, please feel free to use the questions panel or the chat panel to reach out to our webinar coordinator. With regards to the agenda, we'll start by first understanding the context behind today's webinar. So we'll look at the energy efficiency standards globally and what that means for different design cycles for engineers. We'll talk about the role of cloud-native simulation in developing energy efficient products, emphasizing the different use cases where SimScale could be of use for energy efficiency studies of water pumps. And the most important part, Omar is going to demonstrate one such use case, taking an example of an end suction closed couple pump and showing the workflow of setting up a simulation in SimScale, using the pump curve data and exporting it to a pre-designed template that calculates the pump energy index using the Hydraulic Institute standards. So why water pumps? Because they're everywhere. And this industry is growing at a solid 5.6% compound average growth rate, mainly driven by a lot of infrastructure and construction activity, and generally a very increase in demand from industrial end user segments. And as you know, pumps are generally energy consuming products, because of which in the last few years, they have attracted a lot of regulations from governments across the world requiring that in order to be marketed in individual countries, they need to have a minimum efficiency. So what that means is that the onus is on equipment manufacturers to make sure that their product lines meet these regulations while also staying competitive in the market. That is to say, reducing the total cost of ownership for their end user. So obviously, this has sparked a lot of innovation and R&D, where there is focus on electrification and solarization, and intense research efforts for hydraulic redesign of existing fleets, and also what is known as the extended product approach, which looks at improving the efficiency of the full pumping system and not just individual components. An overview of the regulations as prescribed in the EU. So EU defines what is known as the minimum energy index, which is the minimum efficiency a water pump must have at best efficiency point, 75% BEP and 110% BEP, resulting in what is known as the house of efficiency. So for a pump to be operated in the EU, the actual efficiency of the tested pump should be above this house of efficiency, and which the minimum being calculated using a predefined table that was collected using data from many pumps. This is in line with the regulation which was passed in 2012, which mandates that post 2015, all water pumps must have a minimum efficiency at these three duty points of at least 0.4. But in reality, most manufacturers try to aim for a minimum energy index of at least 0.7. And this resulted in a test standard 16480. And what it means is that pumps that satisfy this test get CE marked, and only those pumps are allowed to be sold in the EU. The US Department of Energy also has similar standards and defines what is known as the Pump Energy Index, which is essentially the weighted performance of the pump being tested with respect to the weighted performance of a minimally compliant pump. It is calculated at either a constant load or a variable load, depending on the type of pump. And similar to the minimum energy index of the EU, it is also calculated at three different duty points, that is best efficiency point, part load, and overload. And hand in hand, the Hydraulic Institute has developed a voluntary energy rating program. This is not mandatory. Manufacturers can choose to comply with this, but what it essentially does is describe an energy rating in a form that is more relatable, that is more market facing, and has a third-party certification behind it. And it's easier to translate the energy rating to savings in power, savings in energy, and cost in terms of dollar value. So higher the ER, better is the pump. So it is clear that there are a lot of regulations, and all these regulations are still evolving. For example, these are expected to be revised in the US, and there are going to be additional regulations on heat circulator pumps. And other countries are also going to follow suit. China is trying to emulate the similar model as in the EU. So what this means is that engineers in the pump industry have to innovate really fast and have to have methodologies in place that will keep up with these evolving regulations, thereby allowing them to design efficient products, get them certified, and bring them to market in a cost and time effective manner. And that's where SimScale comes in. Those of you who are new to SimScale, we are the world's first truly cloud native simulation platform. And through our web browser based simulation interface, our aim is to empower every engineer to innovate faster by making simulation technically and economically truly accessible at any scale, at any location, and at any time. With respect to energy efficiency studies of water pumps, what that means is that you can use our cloud native architecture to do a lot of initial design verification and validation, including automated pump studies to understand the pump performance curve and the flow characteristics of a given model. Engage in iterative design where you change operating conditions, you change geometric design parameters. Also optimize your pumping systems, leveraging the API integration that is allowed by SimScale, connecting to third-party tools. And finally, design validation to see if the design that you have come up with complies with the energy efficiency regulations. If not, you can repeat this cycle iteratively, much faster than you can possibly do through physical prototyping or on-premise software. And behind this are proprietary CFD methods, which are well validated and come close to 2 to 5% accuracy of test data, cover a range of physics, and have inbuilt visualization so that you have an end-to-end simulation experience all within your web browser. And you can leverage the unlimited parallel simulation platform to launch multiple design of experiments simultaneously. And you can connect them to your existing workflows, existing CAD design and optimization tools. So that's about how SimScale can be a powerful tool to have while designing energy efficient water pumps. And to emphasize this point, I'm now going to hand over to my colleague Omar, who will show a specific case study for the pump energy index calculation of an end suction closed couple pump. And one point to be noted here is that the workflow that we are showing right now is not limited or it's not limiting in any manner. It's just chosen for this brevity of time that we have. But similar workflows can be extended for other types of pumps, other types of problems or energy efficiency calculations using the same example and same workflow. So over to you, Amar.
Thank you, Kanchan. Hello, everyone. So, really quickly, what I'll do here is I'll give a quick overview on the case that we're looking at for this webinar. We're going to be looking at an end suction close-coupled centrifugal pump, looking at the design performance of a baseline design with a 5-blade impeller, and looking at designing an impeller that works under the same duty points, the same operating conditions, but with a 6-blade impeller, and comparing the energy efficiency of those two designs. The two designs were made within CF Turbo. Thanks to a new release of CF Turbo, we can now push these geometries from their platform to be simulation ready to work with SimScale directly. So here's a quick overview of the kind of operating conditions we're working with. Just regular atmospheric conditions for the inlet condition at 0 gauge pressure, and outlet conditions of 21.5 to 57.5 meters cubed per hour. These two impeller designs, these two pump designs were designed to have a best efficiency point around 36 meters cubed per hour, or about 1 liter per second. So this is going to be a low speed impeller, so around 1800 RPM. And just to define the physics of what we're simulating, we're working with water, fresh water, so incompressible flow, modeling full turbulence, and working on a time steady state time dependency for this setup. Let me go ahead and quickly shift over to the SimScale platform to give an idea of what the workflow to set up these simulations look like. So here we're looking at the post-processing view of a completed simulation. So we're looking at the cross-section here really quickly of one of our, this is one of the operating conditions of the 6-blade design at its best efficiency point. So this is the operating condition of 36 meters cubed per hour. This post-processing view allows us to quickly and intuitively understand the flow behavior within the system so that we can see the how and why it's performing at the conditions that it does. So some notable things that we can quickly investigate here are on the diffuser side, we can quickly see that the velocity is concentrated on the closer half of the screen. So there's not a uniform flow distribution leaving the pump. But we can also quickly see this by changing the flow contour to be a velocity flow contour so that we can see that distribution of flow speeds. I also want to quickly show off if we were interested in looking at suction pressure performance, we can look at the pressure distribution coming into the inlet and see how much the pressure drops near the inlet as the pump operates. So we can look at that cross section here by just changing the cutting plane and looking at the pressure distribution at the inlet coming in. If we wanted to investigate cavitation properties of the operating condition, we can generate an iso volume to look at the gas volume fraction in the flow region to see the extent of the cavitation. In this case, the severity isn't too bad, as the highest gas volume fraction we can see here is about 4%, or 0.04. Let me go ahead and take a step back and actually walk through the simulation workflow. So as I mentioned earlier, we have our two centrifugal pump designs, both designed to operate at a best efficiency point of 36 meters cubed per hour of flow rate. This is the baseline 5-blade design, and we have our 6-blade design here as well. Let me go ahead and walk through the setup really quickly. So as we create a simulation for one of our geometries, we want to use the proprietary Sonic solver. This is our rotating machinery solution for within SimScale. So as we create a new simulation setup, we could just want to go down the tree to define the problem fully. So in this case, we want to go ahead and define water as our flow material, assign it to the flow region, assign the reference pressure on the inlet. In this case, I'll assign 0 gauge pressure, and then the flow rate on the outlet. Now we can parameterize this flow rate so that we can generate that pump curve that's necessary for us to determine the efficiency index. In this case, I'll just define 3 flow rates here. And lastly, we want to quickly define the rotating zone. Essentially, the cylinder is encapsulating the impeller region, and we want to give a moving reference frame to rotate this impeller at the given operating speed. So here what we'll do is assign the appropriate rotational axis, which is in the positive Z or negative Z, up. And then roughly 188 radians per second to correspond with 1800 RPM. The last important step here is if we want to actually extract the results of interest, like the pressure difference across the impeller, as well as the shaft power required to rotate the impeller at given operating conditions. We want to design our result controls. Our important ones are going to be the static pressure difference to generate the static head generated, as well as the forces and moments. Essentially, what we'll do here is just select all the impeller surfaces so that we can quickly extract the power requirement to rotate the impellers at their given operating speed. Now, if I go ahead and kick off the simulation, we'll see that we get an experiment set up and we'll get an estimation of how long that simulation will take. So as I kick it off, we'll set up those 3 operating conditions at those 3 different flow rates. You can parameterize any single operating condition, whether you want to look at various different speeds or various different velocity conditions, or if you're interested in the various different pressure inlet conditions, you can also parameterize your simulation based on that. Looking at a completed simulation or a completed experiment of simulations, we can look at we've generated a pump curve for and are able to plot out the power requirement for all the different operating conditions by opening the forces and moments result control. So here we can see the power required. In this case, it's in units of watts, and the negative value signifies a power requirement rather than a positive value, which would correspond with power generated for a turbine, for example. And then if we look at the pressure difference result control, we're able to look at the static head in units of pascals. So these result controls can be exported out as a CSV file and plotted into an Excel or spreadsheet so that you can continue to work with generating that water pump efficiency index. In this case, we'll work with the pump energy index, the index that's based on the US DOE standards. So here's a templated workflow for to work with that calculator. Essentially, we need to define the we need to input the pump curve data that we've generated from SimScale. In this case, I've input it all down here, so we can look at the use the appropriate units that are relevant in the calculator. So that's going to be flow in gallons per minute, head pressure in feet, and then power requirement in horsepower. So all those conversions are applied here for the 3 important duty points. And if you wanted to if you wanted to include an overload condition past 110%, you can also include 120%, which allows you to input more information to get a better idea of your efficiency breadth for your pump. So after inputting all the information here from your pump curves in SimScale, we're able to open the Hydraulic Institute Pump Energy Index calculator. So going here, we can see going from the first step, these first 4 inputs are just for you to actually work towards a certification. So these are not required inputs, but we want to input the necessary parameters to define what category this pump fits in to define the appropriate energy index model to it. So in this case, we're simply just modeling the pump, but we can also model the full system of the pump, including controls and the motor. In this case, because we're modeling the bare pump, we're only interested in a constant load condition. We input the dimensions and the nominal speed of rotation based on what bucket of rotational speed the impeller is rotating at, whether it's high speed or low speed, and the number of stages we're testing. In this case, we're working with an end suction closed coupled pump, and we're going to be testing the 3 flow rates, the 3 operating conditions: 100% of best efficiency point, 110 and 75%, and then looking at the pump power requirement at 120% to understand that loading condition. So going to that spreadsheet and pasting your information here based on your design's performance, we can calculate the PEI. Now, this is the pump energy index that we generated for the 6-blade design by inputting all the information from our spreadsheet here. So just to review the performance of these two designs side by side, the 5-blade design and the 6-blade design, looking at their best efficiency point, we can see the comparison of how the pressure develops across the pump and what the maximum pressure or head is developed based on these two designs. So we can see that just based on the contours alone, we can see that the performance of the 6-blade design generates a much higher head, closer to that of roughly a doubling of the pressure ratio, or at around 100 kilopascals. But to look at the entire performance and looking at the parameters that are relevant in terms of the energy index, we can see that the efficiency, the peak efficiency for these two designs is offset by about 2.5%, while the static head grows from 9.38 meters to 9.93 meters at that best efficiency point, and this results in a significant improvement in the pump energy index rating. Just for completion, here's the generated pump efficiency curve. In this case, we're looking simply at hydraulic efficiency, not interested in looking at the full system, but that of course can be included within your workflow. To reiterate on how you're actually modeling this energy efficiency index, we're looking at that best efficiency point for each design and looking at a wide range of operating conditions to understand the head generated and the horsepower requirement of the pump impeller motor to transmit into the pump impeller, looking at all those conditions to generate the energy efficiency index. And just for completion, here's a comparison between the 6-blade and 5-blade design for static head curve. In this case, the 6-blade design is the red curve, and that's the same case here for the hydraulic efficiency. And then lastly, the shaft power requirement. So there's more power required, of course, with an additional blade and additional surface to rotate, but that comes at the benefit of enough head generated as a result of that, such that the efficiency grows across the duty points of interest here. But yeah, with that, thank you so much for watching the webinar today. If you have any questions, please feel free to leave them in the chat. Be more than happy to help answer any questions.
Yeah, I can. So we do have some questions, and thank you, Omar, for covering the workflow. The first question being, how is the comparison of CFD and test results?
Yeah, that's a good question. So the nature of simulation is always going to be, there's always going to be some margin of error working with models that are not necessarily designed for production and don't have the clearances and seals that you may have in your final design. But aside from that margin of error, we're usually seeing 2, 5, 7% margin of error between test data that is generated, excluding external systems like the motor efficiency and such, to the actual simulation data that we generate within SimScale.
Yes, so I'd have to agree with Umar that typically it is under 10%, and for comparing designs especially, it is pretty darn close. We do have additional. What type of turbo machinery can this solver handle? Maybe I'll take that question, Umar.
Sure.
Yeah, so it can handle all types of centrifugal, radial, and axial turbo machinery. At the moment, within SimScale, we do not have the capability to handle positive displacement type of machines, but we are working on that, and maybe within the year we will also release that capability. And also in terms of physics, for all kind of centrifugal turbo machinery, we can handle multi-phase flows, cavitation, real gas properties, heat transfer. So all of that is available. I hope that answers the question. And I had Okay, one more. Can we import CAD like from Fusion 360 SolidWorks? I think that's better for you to answer, Omar. 'Cause you do this all the time, right?
Sure, yeah. So working with Fusion 360, that's definitely supported. A lot of different CAD native formats are actually supported. So Inventor and Fusion 360 from the Autodesk suite, SolidWorks, Creo. A lot of file formats are accepted within their CAD native form, but you can, if you're working with a more niche CAD tool that may not be supported natively, you can also export your files to a geometry generic file format. So those are things like SAT, step files, IGES files, and the like.
Thanks, Amar. Uh, we do have a few more minutes and we can take some additional questions. And I have one here that was submitted actually before the webinar. Um, how would you predict changes in pump efficiency based on changes in suction head pressure? And is there a way to find out the optimum suction pressure for most energy efficiency? So for this, Umar, I believe you did touch upon how to visualize suction pressure. Maybe we can also quickly look at how you can parameterize and get a variation of your performance as a function of suction pressure.
Yeah, absolutely. So the same way I've parameterized across several different flow rates. If I'm interested in looking at how suction head can affect the efficiency, I can look at one single duty point, one operating flow rate, and look at the various different suction heads that it operates under to see generate a curve at that one flow rate to be able to understand the best efficiency with respect to the suction head.
What is the cost of SimScale software? Uh, that depends actually based on what modules you are um, you know, actually subscribing for. And that is a question that is best answered by our sales team. If you're interested, uh, please get in touch. Either you can sign up directly on our website, upon which you will be able to start using the software immediately, what we call as the community plan. You have to know that within the community plan, your projects will be public and therefore viewable by everyone. But you can experience the entire software, almost the entire software within the community plan. And if you wish to upgrade to the pro features, the best way would be to get in touch with our sales team. Another question, how did you compensate for impeller rotation and how accurate is it?
Sure. So the appropriate model we use for the rotation of the impeller is the moving reference frame model for steady state simulations and a MGI or mismatched interface for the transient models. So this rotation is simply modeled by encapsulating either using a conformal body or like a cylinder like I've done around the impeller rotating surfaces so that those are encapsulated with some clearance and then we can rotate that reference frame with respect to the inertial reference frame of the entire model. So that's how the rotation is modeled within SimScale. So it's fairly seamless and pretty intuitive to generate that rotational body. You're just enveloping those rotating faces within the model.
Cool. Thank you, Mar. And I think we have time for just quick one question more, I guess.
Sure,
Can SimScale model fluids with suspended solids? And I'll take that one as pretty quick.
sure.
The answer is not yet, but we're getting there pretty soon. Okay, and
Just to touch upon that,
mhm,
we do have a roadmap page within the SimScale website. So if you wanted
yeah,
to see if a feature or capability is within the coming months, then you can see that yourself. But if it's not, or if it's not necessarily planned, you're able to submit your own feature requests within that same roadmap website. And I believe that's just simscale.com/roadmap, but don't recall off the top of my head.
cool. Okay, I think we are at the top of the hour. Unfortunately, we won't be able to take more questions, but we do have them all archived here within the webinar room, and we will get back to you via email if we could not attend to them now. Thank you so much. Thank you so much for attending. Thank you so much for your wonderful questions. It helps us to learn a lot too. Have a good day.
Thank you, everyone. Have a good one.